In this section, we are going to discuss a special category of matrices called elementary matrices. To kind of understand and justify this special category of matrices, I want to start with this theorem. So let's let A and B be matrices. Okay, A is an m by n matrix, B is an n by k matrix. And let C be the product of those two matrices. We know the product is defined because the number of columns of A is equal to the number of rows of B. So C is going to be an m by k matrix, right? M rows, k columns. Suppose we apply an elementary row operation to A to obtain A prime. And we apply the same elementary row operation to matrix C, the product matrix, to obtain C prime. Then C prime is equal to A prime times B. In other words, applying the elementary row operation to the product after we multiply is the same as applying the elementary row operation to just the left matrix before we multiply. Okay? So let's prove this. So since we're talking about matrix multiplication, I want to focus on the rows of the left matrix in the product, which is matrix A. So let's let A be the matrix with rows R1, R2, all the way to, I have M rows in matrix A, so all the way to Rm. And we're going to let matrix B be the matrix with columns C1, C2, all the way to CK. Then note that the IJ entry for matrix C, which is the product matrix AB, is the dot product between the ith row of matrix A with the jth column of matrix B. Okay, we've seen this before. This is just how we define matrix multiplication. The product matrix, the entry in the ith row and the jth column, is just the dot product of the ith row of matrix A with the jth column of matrix B. That's just what matrix multiplication is. Okay? So what we want to do here is we want to consider each kind of elementary row operation one at a time and prove that this property holds. Okay? We have three elementary row operations. We can swap two rows. Right? We could swap two rows. We can multiply one row by a non-zero constant. And we could add a multiple of one row to another row. Okay? Now, I'm actually only going to prove one of these. We'll only look at this last one here. The other two can be proved very similarly. Okay? Suppose, actually, let's say consider. Consider the elementary row operation where we take a multiple of one row. I'll call this row I1. Add it to another row, let's call it I2, and store the results into that second row. Okay? if we apply this elementary row operation to matrix A, the resulting matrix A prime will have and so what we're doing is we're applying this matrix to matrix A. So if we apply this elementary row operation to matrix A, then in row I sub 2, we'll have in row I sub 2 the vector. So we're going to take k times the vector in row I sub 1, right? And we add it to row I sub 2. And that's my new row I sub 2. Okay? All the other rows stay the same. The only row I'm changing would be row I sub 2. Okay, whatever I sub 2 is, right? The idea here is I sub 1 and I sub 2 could be any two rows. Okay, so I've just changed one row, row I sub 2. Okay. And A prime is my new matrix. Okay, after I apply that elementary row operation to matrix A. Now what I want to do is I want to show that A prime B is equal to C prime. So I'm going to do the thing I usually do when I'm showing two things are equal. I'm going to calculate what happens on the right side. I'm going to calculate what happens on the left side and show that I get the same thing. Okay. All other rows of A prime are the same as A. Then what we're going to do is we're going to think about the product matrix A prime B. And I want to see how what the result looks like in A prime B. Okay. Then each element in row I sub 2 of the product, remember to find a product, you take the row of the first and take the dot product with the column of the second. So each element in row I sub 2 has the form. And so I'm going to take the element in A prime in row I sub 2, which looks like this. So k row I plus row I sub j. No, I sub 2. Okay? So I take this row from A prime because that's the element, that's the row in row I sub 2 after the elementary row operation. And I'm going to take the dot product of that with a column in matrix B. Okay? So actually, let me be a little clearer here. That is what we do. But let me be a little more specific here. Then the element in row I sub 2, column j, so the I sub 2 column j element of A prime B is, just as I said, it's going to be the I sub 2 row of A prime B. We did the elementary row operation to row I sub 2. This is the new row I sub 2 in matrix A prime. So I take that row, and I take the dot product of that with the column, the jth column of matrix B. Okay, and I could distribute this, right? Dot product has a distributive property, so I get C row I dot Cj plus, row I1 plus row I2 dot Cj. All right. So that's the I sub second row of our product matrix A prime B. And here we applied the elementary row operation just to matrix A first to get A prime, and then we multiplied that by matrix B. Okay? All the other rows, so for all other i's not equal to that I sub 2 row, the product stays the same because I didn't change the row, right? All the other rows of A prime are the same as A. So for all the other rows, all the other indexes I that are not that I sub 2 row, the ijth element of A prime B stays the same. It's still just the dot product of the ith row with the jth column. Okay? Okay, so hopefully that makes a little bit of sense. I know it's a little confusing because there's so many moving pieces here, but we've considered the right-hand side, okay? And we know that after applying the elementary row operation to A and then multiplying the matrix by B, the row that we applied the elementary row operation in, this is what each element in that row looks like in the product matrix. All the other rows in the product matrix look exactly the same. Okay. Now what we want to do is we want to consider the left-hand side of the equation. We want to show that we get the same thing. Okay. Next, let's consider C prime. So remember, C prime is when we apply the elementary row operation to matrix C, our product matrix. And we know each entry of our product matrix is just the dot product of the row of the first matrix, matrix A, with the column of the second. So if we apply the same row operation, so that was K R row I sub 1 plus row I sub 2 and store the result in row I sub 2, to matrix C, we find that the I sub 2j entry of matrix C prime, the matrix where we've applied the row operation to, is, so here, remember, this is each element in matrix C. Okay, so we want to take to apply the elementary row operation, we want to take K times the element in row I sub 1. So I'm going to take k times the element in row I sub 1. So row I sub 1 times the column we're in, or dotted with the column we're in, plus, now take the element from matrix C that's in row I sub 2. And just applying what we know about the product matrix, this is going to be the element in row I sub 2 in whatever column we're in. Okay, again, I'm just taking the fact that this is the ijth entry of our original matrix C. So all I'm doing is swapping the row numbers, and so I'm just plugging in the row number here to get the element that I want. Okay, so when I'm looking at row I sub 1, ri sub 1 dot cj. Okay, when I'm looking at row I sub 2, the element in the jth column for this row is ri sub 2 dot cj. All right. This is the only row that changes, row I sub 2. So we've looked at the entry for row I sub 2. Let's look at all the other entries. For all other rows, for all other indices I, which aren't equal to that row that's changing, okay? The ij element of C prime is the same as C because we didn't change it. Namely, it's ri.cj, which again, that's just the same as the ijth element of matrix C. Okay? Okay, so we applied the elementary row operation to matrix C to get our new matrix C prime. Okay, in row I2 in every column, this is what the entry of row I2 looks like. Okay. For all the other rows, we didn't change anything. We only changed row I2, so we just kept the same element as we had in the original matrix C. Notice now that if we go row by row, we have the same elements in both matrices. For all I not I2, in our product matrix A prime B, we have ri.cj. That's the same thing in C prime. For all I not equal to I2, if we look at element ij in matrix C prime, we have the same thing, ri.cj. Okay? The real interesting thing is the row that we apply the elementary row operation in. So if we look at the each entry in row I2 in column J, so the I2 comma J element, then each entry there has this form. Some constant times row I1 times r sub I1 dot C sub j plus r sub I2 dot C sub j. Okay? If we look at the same row in matrix C prime, okay, so this is the, so we're looking at each entry in the I sub 2 row in the jth column of matrix C prime, the matrix after we apply the elementary row operation. We get the exact same structure. Some constant k times ri1 dot cj plus ri2 dot cj. Okay, it's the exact same thing. Thus, C prime is equal to A prime B, and we're done. Okay, so understanding the wording of the proof can be a little complex. Oh, and actually, I should say, we only proved one elementary row operation here. But the other elementary row operations can be proven similarly. You just look at how the elementary row operation would affect C prime. and compare it to how the elementary row operation, what happens with A prime B. Okay, so just to sum up again of what we just proved, the proof is a little wordy. It can be hard to follow the wording. Okay, but try to understand the theorem itself. Matrix C is a product of two matrices. What it's saying is it doesn't matter if we apply the elementary row operation to A times B after we multiply them. Okay, that would be the same as applying the elementary row operation to matrix C at C prime. Or, let's see, let's go elementary row operation. Okay, if we apply it to the matrix A times B, or if we apply it to matrix A first and then multiply by B, it gives us the same thing.